All right, guys, welcome to Quarantine Statistics, Day 4 with Mint, the cat. Today we're going to be working on a couple of those problems that we introduced on Monday. There's like 3 or 4 problems there that run the full gamut of exponential stuff. So this will be the last we do with exponential equations. We're going to do one problem as an example together, and then you guys will have a couple problems to try out on your own. But then tomorrow, we'll be moving on from exponential. All right, what we're going to be working on is example 4. This is on the next page of your packet after what we were working on Monday. So what we see is a data set here, and it says the data at the right shows the cooling temperatures of a freshly brewed cup of coffee after it is poured from the brewing pot into a serving cup. The brewing pot temperature is approximately 180 degrees Fahrenheit. So we see the data there, and then it wants us to draw a scatter plot of it. So what I did is I put the data into the lists on the calculator, like so. And then I drew the scatter plot by hand, but we can double check in the calculator to make sure that's what it's supposed to look like. So the deal is, first off, when we draw the scatter plot, we want to label the axes. We have time versus temperature. I will say I don't love the graph that they gave us here because all the values are positive, but it gave us a 4-quadrant graph. It would have been much easier and much less painstakingly small to draw if we could have used this whole graph and not just the first quadrant there. But, well, I don't know why they made that decision. We can check the graph, though, in the calculator by hitting Zoom and going to option 9, and we see that ours looks approximately the same. So, one thing, apologies for the sneeze. Hopefully, not coronavirus. So, what we see here is that I did have to scale the axes a little bit. We go 0 to 50 here, so we were able to start at 0, but I went by 5s just to make sure I got all the way up to 50, which was my highest x value point. And then over here, I started at 100 instead of 0 because my data set only went from 100 to 180. So I had no real reason to include 0 to 100 there. So I went by 10s so that I could get all the way up to 180 on the y-axis. So there's my scatter plot. Now what I want to do is the other parts of this problem. B says find the exponential regression for the function. You guys should know how to do that by this point, but just for the sake of me walking through this, we're going to go stat calc and then option 0 for exponential regression. And then we find that y equals a times b to the x power. Apologies, I am working with a relatively small span of space here. We get y equals 171 times 0.988 to the x power. And there is our exponential regression. Now the next question says, how closely does this function describe the data set at the table? How do you know? So what's important here is whenever we talk about how closely does this describe the data set, that's kind of like the same thing as asking how good is this equation as a predictor of the data? How reliable is this equation? And that's where our r squared value comes in right here. And r squared in this instance is equal to 0.97, so it is a very good description of the data set. You may actually be looking at this and saying, that's not what I thought exponential looked like. I thought exponential went like this, slow and then rises up real high. That's what exponential often looks like, because in most situations in the world, most data that we're tracking, we are looking at data that has a slow beginning, much like the coronavirus stuff that we were tracking. Things start slow and then they start to really accumulate, like a snowball effect, right? That's often the way we see exponential growth. But it is possible to see something like this that's called exponential, well, I guess not exponential decay. That would be the opposite of logarithmic. Sorry, I almost gave out the wrong term there. But we see the opposite version of that. We see a very rapid decline and then kind of a leveling off there. So it is possible for exponential graphs or exponential lines, exponential relationships to go the opposite of how we're used to seeing it. If you do not have r squared on your calculator, just FYI, the way to get there is to hit, sorry, trying to make sure I have this all on screen. You hit second 0 to go to the catalog, and once you're in the catalog, you can just scroll all the way down, and it may take a little while, until you get to something called diagnostic on. So we're going down, there we go, diagnostic on. You hit enter on that twice, and that will get your r squared values turned on if they're not already there on your calculator. Okay, so moving along. Interpolate, according to the model, when is the coffee at a temperature of 106 degrees? So what we can do is we can take a look at the model here and see we have y equals 171 times 0.988 to the x power. And we know x is representative of the amount of time that has passed. Y is representative of the temperature. So if we want to know when is the temperature going to be 106 degrees, we can plug that into our equation. So I'm going to do that. 106 equals 171 times 0.988 to the x power. Sorry, I was writing off screen there. I think I need to get my camera more elevated. It's not showing as much as usual. So we plugged it in for y because that's what represents temperature, and because we're looking for time, and x represents time. So it makes sense that that is our variable that we're looking for. So we want to get this x on its own. We are going to remove the 171 from the equation first by dividing by it. So we get 106 divided by 171. And we end up with 0.620 equals 0.988 to the x power. As we know from our lessons earlier, whenever we have an x in the exponent or a variable in the exponent, what we need to do is apply a logarithm to both sides so that we can power rule this. Log of 0.620 equals log of 0.988 to the x power. When we have that x in the exponent, it can be brought around as a coefficient, meaning that we could really write this as log of 0.620 equals x of log 0.988. And that will allow us, now that the x and the logarithm are separate, to divide by the logarithm of 0.988 to get x on its own. And remember, whenever you type this into your calculator, that when you put in a log for 0.62 in this case, you have to close those parentheses to make sure that everything is calculated correctly. 0.988, and we get 39.5 or 39.6. So that tells us the number of minutes for it to reach 106 degrees is approximately 39.6 or 40 minutes. However you want to round that is okay. So x equals 39.6. Now we can check to see if this makes sense with our data. At 39.6, right about here, almost at that 40-minute line, we're seeing a point right around 110-ish, and our goal was when is it going to be at 106? So that seems pretty realistic to me to assume that a point right about there in the data set would make a lot of sense. All right, so we got that. The final question says, what is the predicted temperature of the coffee after 1 hour? So again, we're going to utilize our equation, but we have to be careful about what we're plugging into it. So if we know our equation is y equals 171 times 0.988 to the x power, we have to think about which one of these variables represents hours. Well, technically, neither of them. But we do have a variable that represents time. So the x represents number of minutes. However, we have our question written in hours. So how do we want to write that number when we're plugging into x? We don't want to write 1. We want to write it as 60 because we have to do that, pretty simple conversion there. So we get y equals 171 times 0.988 to the 60th power. We unplug that into the calculator. 171 times 0.988. This button right here will go to the 60th power, or put you up in the exponents so that you can write the 60th power. And then we hit enter, and we get 82.9 degrees. That would be the temperature of the coffee after that amount of time. So this was example number 4. You have a pretty short and brief example number 3 right above it, as you can see right there. And then on the following page, there is an example 5. Ooh, the example 5 is actually the logarithmic regression. Nice. I really thought that was another exponential one. That's my bad. So what we'll do is you can try out example 3 here, and then tomorrow we'll work on the logarithmic regression. But if you have any questions, feel free to let me know.